Right. Well, today, if I'm not mistaken, Ben Andrews is going to talk about these harmonic functions with polynomial growth by Colding and Minicozzi. Is that correct?
Yeah, thanks, Paul. More or less, yeah. I'm going to talk, I think, for 2 weeks, and that's the main result that I want to get to. I'll start out a bit more gently, though. I'm going to talk a bit more about sort of some of the background on harmonic functions and some of the tools that we need on manifolds with non-negative Ricci curvature, things like that. So yeah, what are we talking about? Harmonic functions. Strange color. Yeah, Paul very nicely put some of the, at least one of the papers which is relevant in the email that he sent out. That's really one of several. So in fact, in that paper, which I think is the one in JDG 97 by Colding and Minicozzi, they prove a result under the assumption of Euclidean volume growth. And then there's actually a later paper which is in the Annals by Colding and Minicozzi, same year, 97, where they do the general result. I'm actually going to work mostly from a paper by Peter Lee. He just found a bit of a simplification of the argument that they used, which is what I'll get to. So that's what we're aiming in the end, hopefully by the end of tomorrow, get to this result. The result is essentially that the space of harmonic functions of polynomial growth on a manifold with non-negative Ricci curvature is finite dimensional, and there's some kind of estimate on the dimension of that space. But I want to start out just recapping some things. So let me start out first with just a few remarks on the Euclidean case. Can everyone see that okay? I'm not quite sure what you're seeing.
Yeah, looks good.
Yep,
looks good.
All right. Okay, so actually Matt gave a nice introduction in his talk about the Euclidean case. I mean, you can think about harmonic functions entirely in terms of this mean value formula, which gives you the value of the function at some point x as the average over any ball about x, or alternatively the average on the boundary of the ball. So Matt gave a nice argument to get from that to the Louisville theorem, but I want to actually just give a slight strengthening of that to give the gradient estimate. So to prove a gradient estimate, you can really work straight with that mean value formula. If I just differentiate that with respect to x, okay, so then let's say compute du of x in some direction e, then I'm moving the point x in direction e. So let me draw a little picture. I have my ball about x, and then let's say we're moving in this direction e this way. Then the rate at which this average over the ball changes is just given by the, sorry, I've got it's really, well, okay, 1 over the size of the ball, which doesn't change. The rate of change of the integral of u over the ball is just the integral around the boundary of u times the normal speed. So that will be, okay, what do I get? 1 over omega n r to the n, which is the volume of the ball. And I get integral around the boundary of u times the normal speed, which is just the inner product of e with the normal, because it's moving in at speed e, and so I just take the normal part of that. So that's the formula for the gradient at x. And let me see, I mean, actually, if I take out, that's really the same as n over r times the average on the boundary of u times the e component of the normal. Okay, so it's a very simple expression for the gradient, and straight away from that you get a gradient bound, right? So if I have a bounded harmonic function, let's say u is bounded by some m on the ball, then straight away from this you get that du is bounded by, so I can just bound this by n over r. The nu dot e is bounded by 1, so I get n over r times the sup of u, which is n. Okay, so that's the gradient bound for harmonic functions, and straight away from that you would get the proof of the Louisville theorem, of course. All right, I can also get the gradient bound for non-negative functions. So if u is greater than or equal to 0 on the ball, then, okay, so again, so I'll get, so it's n over r average over the boundary of u nu dot e, and nu dot e is less than or equal to 1, so this is less than or equal to n over r. I'm using here the fact that u is non-negative to do this inequality. So I just get u. Okay, so here that would be true if e is equal to the direction of the gradient, for example. Right? Then, yeah, and then that's just n over r times u at x. So that it gives you directly this logarithmic gradient estimate. So that in other words, if you have a non-negative harmonic function, then the derivative of the gradient, or du of x divided by u of x, is no bigger than n over r at the middle point. Okay, and that gives you the Louisville theorem for non-negative harmonic functions, because if I take r going to infinity, then this gradient goes to 0. So the function is constant. Okay, so let me just mention, so this implies the Louisville theorems for bounded or non-negative functions. Of course, the non-negative one implies the bounded one.
Ben, can you also exploit the fact that the gradient in the direction E is harmonic in this argument?
Essentially, that's what I'm doing. Yeah. The other way to do that would be to observe that du dxi is harmonic and plug in the formula. That would give you an integral around over u of du dxi, and then you can integrate by parts to get the formula on the boundary. You end up with the same formula. Right?
Gotcha.
So you can derive that several different ways. Yeah, thanks, Matt. Okay, so this one, yeah, okay, that'll do about that. So yeah, let me prove then the kind of the Euclidean case of this main result that we want to prove. So the theorem, well, in this case, it follows from this result. So harmonic functions on Euclidean space of polynomial growth are in fact polynomials. And it follows, of course, you can count the harmonic polynomials easy enough, and that gives you a bound on the dimension. So in other words, let's define this space HP of Rn. This is space of harmonic functions of polynomial growth. So this is just, let's say, functions which are, well, I might as well say C infinity Rn, which are harmonic, Laplacian equals 0, and have a volume growth bound. So that u at any point x is bounded by some constant times, let's say 1 plus the length of x to the power p for some c. Okay, so yeah, the claim is that this consists of the harmonic polynomials of degree up to p. Okay, so the key step in proving this is essentially the observation that Matt just mentioned, which is that if you have a function on Euclidean space which is harmonic, then all of the partial derivatives are also harmonic. And really the lemma is that if you have one of these functions of polynomial growth, then each derivative, so du dxi, is also harmonic, but it's of growth 1 degree lower. So it'd be hp minus 1. Let's say at least if p is greater than or equal to 1. And the Louisville theorem, in fact, or du dxi vanishes if p is less than 1. So that just comes from the gradient estimate that I proved. All right, so let's prove that. It's really just a simple application of the gradient estimate. So if I have x, which is in, let's say, the ball of radius r about the origin, then we get the gradient estimate, which says that du of x is bounded by n over r times the sup on the ball of radius r about x of, well, mod u, I guess. And the polynomial growth estimate, we can plug that in. So now let's see if I choose, okay, in general, this would give you n over r, and then the polynomial growth bound says this is b1 plus r plus mod x would be the sup on that ball of radius r about x. Okay, so now if I choose, let's say, mod x equals r, so r equals mod x, in other words, choosing r, then that says that du of x, and in particular each of the partial derivatives, is bounded by n over r. So I get his c 1 plus 2r to the p. And so as long as r is bigger than 1, this is bounded by some constant times 1 plus r to the p minus 1. Okay. So that's enough to show that it's in this hp minus 1 space. Okay, so very simple observation. Really the same argument as in the proof of the Louisville theorem, except instead of taking r going to infinity, we just choose a suitable r depending on how far your point is from the origin. And I won't go through the p less than 1 case. That's straightforward, I think. So a corollary of that is that if I differentiate enough times, then I'll get down into an HP space with p less than 1. So it's, in other words, let's say if u is in HP, then you get that any case derivative, let's say, is is 0. I guess is what I want to say. If k is bigger than p. Okay, and that tells you straight away that u is a polynomial. Okay, so really there's very little work to be done here. Just comes directly from the fact that if you have a harmonic function, then all of its derivatives are also harmonic, and you can control their growth. So it's not a big deal in the Euclidean case to prove this. It's really pretty straightforward. Let's do a dimension count. The dimension of the space of harmonic polynomials in Rn. Okay, so it's actually given by this formula. You n plus p minus 1 choose n minus 1 plus n plus p minus 2. Choose n minus 1. And if you work that out, that is, well, it's sort of asymptotic to, what is it, 2 over n minus 1 factorial p to the n minus 1, at least for p large. Okay, so that's the kind of the Euclidean case. All right, so really the big result which we're trying to get at is generalizing that to manifolds. If you want to generalize this finite dimensionality to manifolds with non-negative Ricci curvature. You can prove something a bit more generally than that, but I won't try and do that. I'll stick with the non-negative Ricci case. So Ricci non-negative, and this is the result by Colding and Minicozzi. So really, the theorem which we want to prove is if you have an n-dimensional manifold, let's say it's complete, non-compact, otherwise the result's kind of trivial. With the Ricci curvature of G greater than or equal to 0, then you get that the dimension of the space of harmonic functions of polynomial growth on M is bounded by some constant which depends only on n times p to the n minus 1. Okay, so we'll take a little while to get that far, and today mostly what I want to do is talk about some background results on manifolds with non-negative Ricci curvature. So really, well, okay, so I want to start with the tool which gets used over and over again, which is the Hessian comparison theorem. I know Tim mentioned this last time, and I'd like to give a few more details of how that works. We have a reasonable number of graduate students here, I hope, so I'm hoping that, well, my aim is really to aim it at more or less the graduate level. Okay, so this says that on a manifold with Ricci curvature non-negative, if I define a function, let's say rho, to be the distance from some chosen point, the x0, then, well, okay, so maybe the simplest way to say it is the Laplacian of distance squared is bounded by 2n, or equivalently, well, more or less equivalently, Laplacian rho is bounded by n minus 1 over rho. All right, so the statement, well, okay, so first of all, it's relatively straightforward to show that this holds where rho is smooth. Okay, and in other words, that means you're away from the cut locus. And there's two senses which it holds even across the cut locus, so really globally. So the first sense, which is useful when you're doing things like maximum principal arguments and pointwise arguments, is that it holds in the barrier sense. And this just says that given any point x in M, which rho may or may not be smooth there, of course, but the importance of this definition is at points where rho is not smooth. So if we're something in the cut locus of x naught, there is a smooth function, let's say rho tilde, smooth, defined near x naught, defined near x, in other words, in a neighborhood of x. Okay, so it lies above rho. Okay, so rho tilde is greater than or equal to rho on this neighborhood. At the point x, you have equality. And the Laplacian of rho tilde at that point x is less than or equal to n minus 1 over rho x, or rho tilde of x. Okay, so that's the first sense, the barrier sense. So it really says that it may not be smooth, but you can touch it from above by something that satisfies this Laplacian inequality. And that's usually sufficient if you want to do maximum principal arguments. You can just replace the rho by the rho tilde in whatever function you want to estimate. The second sense in which it holds is the distributional one. So this is important if you're integrating functions of rho. So this you get, so it's, in other words, a weak version of the inequality, which makes sense even where it's not smooth. So you can say if phi is, let's say, a compactly supported function on M, smooth function, and let's say that it's non-negative, then you get, okay, so you can look at the integral over M of Laplacian phi times rho squared. Okay, so if everything was smooth, you'd integrate by parts twice, and you'd get phi times Laplacian rho squared, and then plug in this inequality for Laplacian rho squared, which is less than or equal to 2n. Here, rho is certainly Lipschitz, so we can integrate by parts once. So we get the gradient of phi in a product gradient of rho squared. And then the statement is that that should always be less than or equal to 2n integral of M of phi. Okay, so that's the distributional sense in which it holds. All right, so I want to say a few words about each of those. Let's see. So the in the barrier sense, the argument for doing that is more or less the following. So a very simple way to prove that is to work as follows. So here's our x naught, that's our base point, and we've got some other point x. So we know that there is at least one minimizing geodesic joining x to x naught. So let's call it gamma. The idea is to construct a family of curves from x naught to all the points near x in a certain way, right? So really the picture would be something like this. If I take any point near x, I want to put in another curve here. This won't necessarily be a geodesic, but all I need to have is some good estimate on the lengths of these curves, right? So the idea is we have some neighborhood here, U around x, such that we connect all of the points in there by curves in a smooth way from x naught. All right, so to do that, you start with an orthonormal basis at this point x naught. And so I'm going to choose that in such a way that the nth one of these points along gamma, and then all of the others, of course, will be orthogonal. And then you can parallel transport along gamma to get, well, at each point, an EI. Let's see, if you have gamma of t, then I'll have an EI of t and an EN of t. Since the curve is a geodesic, the tangent vector is parallel, and so the EN will always be the tangent vector at every point. Okay, and then using that parallel basis at each point, I can construct a family of curves. Okay, so now I want to take gamma. This will depend on n parameters, so S1 up to Sn and t. Okay, and that's supposed to be, the S1 to Sn is supposed to be a parameterization of a neighborhood of X, so this neighborhood U. Okay, so it should be some n-dimensional space. And we define gamma this way. So I'm going to take I'll go along gamma for distance. Okay, so here X is going to be gamma of D, where D is the distance, right? So here I'm going to take T times D plus Sn. Okay, so the Sn variable is going to be the one that moves me backwards and forwards along gamma. Okay, so I'll start at that point and I'll move in the direction. So sum I equals 1 to n minus 1, and I'll take T times Si times Ei at the point, the corresponding point, T times D plus Sn. All right, so what does that do? The picture is something like this. It really, the T factor means it's moving away from gamma at linear speed. So it really looks like one of these curves here. Okay, and it's moving in the direction Ei at each point. Yeah, for distance t times Si. Okay. All right, so the endpoints. So the endpoints of these, so gamma S1 to Sn1. So let's call that. So that's just a function of these n variables. Is a diffeomorphism, so that's easy enough to see, to a neighborhood of X. So then, okay, so I want to construct this function rho tilde. I'm just going to take rho tilde. It should be, so I want it to be bigger than rho. I'm going to take it to be the length of the curve gamma at C inverse of Y, right? And then, T, right? Okay, so for each point Y here, this C inverse tells me which values of S1 to Sn to choose to hit that point Y as its endpoint. And so I have this curve, that's so this one here is a curve from X naught to Y. I just choose the length of that curve. Now, since that is a curve from X to Y, the length is of course greater than or equal to the distance from X naught to Y, which is our rho of Y. Okay, so that gives the inequality that we need. And you can also see that when the S's are 0, which corresponds to hitting the point X, then the gamma is just our original gamma, so it's a minimizing geodesic, and so you have equality. So, so it's also easy to see that rho tilde of X is equal to rho of X. And the last thing we need to check is this inequality on the Laplacian of rho tilde, and that just comes from the second variation formula. So the Laplacian of rho tilde at X, the second variation formula gives you that that's sum I equals 1 to n minus 1. The distance along the geodesic is linear so the Sn direction doesn't come into it. So I get integral 0 to 1. And okay, so it's the derivative of the gamma dsi squared. And I get a 1 over d there. and then I get minus curvature in direction, sorry, d times curvature in direction gamma prime, d gamma dsi, gamma prime, d gamma dsi. Okay, integrated from 0 to 1 with respect to t. And now with this choice, the d gamma dsi is just t times ei, and sorry, is the d gamma dsi is tei, and so the derivative of that in the t direction is just ei. Okay, so then this gives me the first term is just exactly n minus 1 over d, and the second term is okay, d integral from 0 to 1 Ricci curvature, because I'm summing over the i's of gamma prime ei, gamma prime ei, maybe times t squared dt. So but the Ricci curvature is non-negative, and so this is equal to less than or equal to n minus 1 over d, which is n minus 1 over rho of x. Okay, so that's the idea, and the point is that since gamma is a smooth function of S1 up to Sn and t, this rho tilde is also smooth, and so that constructs exactly the barrier that we need. For the second part, the distributional sense, that's a little bit easier actually. Remember, what we have to prove is that if I take d phi times d rho squared, then I get an inequality. Okay, so I'm going to use a little bit the fact that, okay, so m is the exponential map from x naught of some set C. So this C is star-shaped. Okay, so really this is, if I start from x naught in any direction, then for small distances, the geodesic is minimizing. Eventually you might hit some point in the cut locus. And so you have in each direction an interval on which the exponential map gives you a minimizing geodesic. And so this C is a star-shaped subset of the tangent space to M at x0. And in fact, you can argue easily enough from the fact that it's just from minimization that it's at least, you know, locally Lipschitz, relatively nice boundary. Okay. So what I want to do here, remember phi is compactly supported. I'm going to write that integral over m as the limit as epsilon goes to 0 of integral over m epsilon, where m epsilon, I'm just going to take to be the exponential map of, let's say, 1 minus epsilon times c. So that means this is what I get by following all the minimizing geodesics, but stopping sort of a proportional epsilon before they reach a non-minimizing point, before they reach a point in the cut locus. So on m epsilon, we have that rho is smooth. Okay. Okay, and the fact that this limit holds is just the fact that the volume of m without m epsilon is small. It's just a simple calculation. Okay, so on m epsilon, I can integrate by parts. So I get integral m epsilon deep C dot d rho squared is, okay, now I get a boundary term. I get the boundary of n epsilon C times the normal derivative of rho squared. But, okay, and then I get minus the term m epsilon C Laplace rho squared, because it's smooth, rho squared is smooth here. So now I can use the smooth case, which we incidentally just proved in this part up here. So I proved this barrier sense of the inequality. So in particular, the smooth point, that means that the Laplacian of rho is less than or equal to n minus 1 over rho. We can plug that in here to make this greater than or equal to 2n integral phi over m epsilon. And this one is, okay, the normal direction is just the radial direction. So d nu rho is 1, and so this is just 2 d c. So in particular, this is greater than or equal to 0. Okay, so then that gives me the inequality. Integral over m epsilon of deep c dot d rho squared is greater than or equal to 2n times the integral of c. And now I just let epsilon go to 0. And integral over m epsilon of c goes to the integral over m of c, since c is smooth. Okay, so that's the distributional sense. So that allows me to deal with integrals involving functions of rho squared and still use this inequality. Okay, so let's look at some of the consequences of this Laplacian comparison theorem. Sorry, did I say Hessian? This is really a Laplacian. Right? The Hessian comparison is the result for the whole Hessian of rho, which you don't get under a Ricci curvature assumption. You need a full sectional curvature assumption to do that. Okay, so the reason, really, the reason that Ricci curvature is a good condition is mostly to do with the fact that you have this Laplacian comparison theorem. So I'm going to show you some of the consequences which are important and which we'll use quite a bit in the proof. So the first one is the volume growth. Okay, so this says, so this is really the Bishop-Gromov result. So let's see, to get this, you can just use this Laplacian inequality. Okay, so I'm going to use that to say that 2n times the volume of the ball of radius r. Okay, so that's just by the Laplacian comparison, that's greater than or equal to integral over m of Laplace rho squared. Okay, so that's simply plugging in that Laplacian inequality. And now, if I integrate by parts, I get integral on the boundary of m of the normal derivative of rho squared, and that's, sorry, not m, what am I talking about? I'm going to do this on the ball of radius r. Yeah. Okay. So on the boundary of the ball of radius r, of course, rho is just equal to r, and so this will be just 2r times the size of the boundary of the ball. Okay, so that gives us, well, some sort of isoperimetric inequality, I suppose. All right, so now if I compute d by dr of 1 over r to the n, the volume of the ball of radius r, then, okay, so I get one term which is just minus n over r to the n plus 1 times the volume of the ball of radius r. And then the other term would be 1 over r to the n times the derivative of the volume of the ball of radius r, which is just the size of the boundary. All right, so then the inequality above, if I plug in that, this would be minus n over r to the n plus 1 size of BR, and then this will give me less than or equal to n over r times 1 over r to the n size of BR. So in other words, it's less than or equal to 0. Okay, so that's really the Bishop-Gromov result. It says that the ratio of the volume of the ball of radius r to the Euclidean volume, which is r to the n, is non-increasing in r. So in particular, from that you get that you can compare, let's say, the volume of a larger ball to the volume of a smaller one. Okay, so this is about some center. I get big R over little r to the power n times the volume of b little r of x, if let's say little r is less than big R. Okay, so that's something which we'll use over and over again. Okay, that's the first consequence. Let's see, how am I going to be time? I'm going to prove, yeah, another consequence which we will need is a Poincare inequality. Okay, so there's various versions of this. I'm going to, well, this is a, I guess, a simplification of a much more general result by Lee and Shane, Peter Lee and Rick Shane. I'm just going to prove the result, the form of this that we need. So let's assume that we have MNG. This has to be, okay, I'm going to make the assumption that's complete and non-compact. And there are versions, of course, which work more generally, say if you have a compact manifold, or if you have a manifold with boundary and things like that. And we need that the Ricci curvature non-negative, of course. Then, so the result is a Poincare inequality on metric balls, right? So it says if I have a function which is, well, let's say, I guess it's enough to say W0, 1, 2 of the ball of radius r about x naught, then you get the integral of the gradient squared is greater than or equal to, so it's some constant which depends only on n divided by r squared times the integral of v squared. Okay, so it's a, if you like, it's a Dirichlet Poincare inequality. Okay, so let's see, proof of that. So I'm going to assume it's enough to prove this for, let's say, compactly supported smooth functions on the ball, and then use the density of those things in the W0, 1, 2. We'll only use it in relatively smooth situations anyway. Okay. Okay, so I want to prove this Poincare inequality. I mean, a Poincare inequality is kind of equivalent to an eigenvalue inequality, if you like. So you can think of this as proving a lower bound on the first eigenvalue for the Dirichlet problem on the ball. All right, well, so, okay, there's a nice little trick. In fact, this is a pretty little argument. So I'm going to look at a smooth function. Probably doesn't have to be smooth. In fact, I'll prove it for smooth things, but then we'll see it actually doesn't need to be particularly smooth in a moment. Okay, so it's going to be smooth and positive on the ball. And it's going to do a little computation. If I look at, okay, integral on the ball, I'm going to compute this thing. So I look at eta squared times the gradient of phi over eta squared. Okay. So if I expand that out, I get eta squared. And this gradient is gradient phi over eta minus phi on eta squared gradient eta. Right? So I'll take that squared. And so that'll give me the first term, which is just gradient phi squared. Okay, that's the thing that I want to estimate here. I want to get a lower bound for this to prove the Poincare inequality. I get the cross terms, which are minus 2 phi gradient phi times gradient eta over eta. Okay, and then I get the square of the last term, which is gradient eta squared on eta squared times phi squared. Okay, now these terms here, the phi gradient phi is just, sorry, the 2 phi gradient phi is just the gradient of phi squared. So I'm going to integrate by parts on that term. So they'll give me a plus phi squared, and then I'll get the divergence of gradient eta over eta. Okay, and that gives me Laplace eta over eta minus gradient eta squared on eta squared, and then the last term again will give me the plus eta squared, gradient eta squared on eta squared. Okay, and so we get this nice cancellation, and what I end up with is this pretty formula. Okay, so gradient phi squared, and then phi squared Laplace eta over eta. Okay, so why is that pretty? Well, if I happen to know what the first eigenfunction was, the first eigenfunction is of course positive, I could plug that in for eta, and then Laplace eta equals minus eta and minus lambda eta, and so this Laplace eta over eta would be just minus lambda, right? So that would give me the sharp Poincare inequality. The nice thing about this formula is now I can get a lower bound for the first eigenvalue, or for the the constant in the Poincare inequality, just by choosing the eta in a nice way. Okay, so it's a useful way to get lower bounds. It only works for the first eigenvalue, but so okay, how do I get? So what I need to get a good result here is that this Laplace eta divided by eta should be something strictly negative, or bounded away from 0. And to do that, okay, so I want to choose eta such that Laplace eta over eta is uniformly negative. All right, so here I'm going to use the fact that we're on a complete non-compact things. Okay, so first of all, if I choose for any, let's say x1, which is not in the ball of radius r, I can let rho be the distance to x1. Okay, and so that will be something which satisfies Laplace rho is less than or equal to n minus 1 over rho. And okay, now I'm going to make things a little simpler by taking minus distance from x0 to x1. Okay, so that's okay, the distance to x1, if I take x to be very far away, then the distance will be large, but taking off this term will make that bounded again. In fact, if I add r, then I'll get something which is positive on the ball of radius r. And then to make it strictly positive, I could add an epsilon. Okay. And so now, let x1 go to infinity. And let's see, so the rows are all uniformly Lipschitz. The gradient of the distance function is bounded by 1. The value at, let's say, x0 stays close to r. And so I get a limit of these. I get a function rho, which is greater than or equal to epsilon on this ball of radius r, and with Laplace rho less than or equal to 0. Okay, this is a very useful tool. This is a thing called the Busemann function. Okay, so this is the point where I use the fact that it's complete non-compact. That just allows me to take my x1 to be going off to infinity. Okay, so once I have that rho, then I can just take eta to be a suitable function of rho. And of course, once I know the Laplacian's non-negative, I can just take a function which is gives me the right inequality. So I can take sine of, let's see, I think I want pi divided by twice 2r plus epsilon times rho. Okay, why that value? Well, rho, in fact, we have rho is greater than or equal to epsilon, but it's also less than or equal to 2r plus epsilon on this ball of radius r. That's just the triangle inequality. So that means that the arguments of rho will stay in the part where sine is an increasing function. Okay, so now if I compute Laplace eta, okay, so what do I get? So I get one term which is, I get pi over 2r plus epsilon cosine, the same stuff, times gradient, sorry, this is the first derivative. Gradient of rho. When I differentiate again to get the Laplacian, I'll get one term which is the same stuff times Laplace rho, and here I'm getting, remember that's the cosine, which is positive. And then I get the other term where I differentiate the cosine, that'll be minus pi squared on 4 2r plus epsilon squared sine times gradient rho squared. Okay, and remember, gradient rho is the gradient of a distance function. That's just equal to 1. Okay, and the Laplace rho is less than or equal to 0, so that gives me less than or equal to minus pi squared over 4 2r plus epsilon squared times eta. Okay, so that's great. So in particular, I get Laplace eta over eta is less than or is uniformly negative. And I get this explicit bound. In fact, doesn't even depend on n. Kind of nice. Okay, so that gives me the inequality. I just plug in that choice for eta, and I end up with the inequality that integral over br of x gradient phi squared is less than or equal to, here if I let epsilon go to 0, I get pi squared over 16r squared integral phi squared. Okay. So yeah, so that kind of illustrates how you would use these the Ricci curvature non-negative. So really, it's very useful for constructing good test functions. Particularly, really, the thing that I used here was that the Laplacian of a distance function has this bound. So I cooked up something with Laplacian rho less than or equal to 0. And that's what I needed to get the right inequality on the Laplacian of eta. Okay, I'm more or less running out of time. The next, yeah, okay. So what I want to do next time is I'll prove. I'm going to prove the Yau gradient estimate for positive harmonic functions on manifolds of non-negative Ricci curvature, and that will recovers the Louisville theorem. Okay, so that'll allow us to prove that, for example, non-negative harmonic functions on manifolds of non-negative Ricci curvature must be constant. And then, okay, so yeah, I was grading estimate, and then that straight away gives you a Harmonic inequality, and then the last thing, the kind of tool that I need is a mean value inequality. Which says something like, okay, I'll just write it down briefly. If V is non-negative and Laplace V greater than or equal to 0, so it's a non-negative subharmonic function, and this is of course on a manifold of non-negative Ricci curvature, then you get V at any point x0 is bounded by the average on the ball of radius r, about x0 of V, times some function, some constant that depends only on n here. Okay, so that'll be, in fact, so the only two things that I need to know in order to prove the theorem on the dimension of harmonic polynomials of polynomial growth, sorry, harmonic functions of polynomial growth, are these, the volume growth bound, the Bishop-Gromov, and this mean value inequality. Whenever you have those two ingredients, the rest of the proof will work. So yeah, let's see, here we go. I'll stop there for today, I think, and then proving those two things might take about half of the remaining time, which means I might actually take a third week to get to the final proof. Yeah. Okay, but that will do for now. Yeah. Any questions?
Yeah, can I ask a question?
Yeah.
So I liked that you went through the barrier and distributional meaning of the Laplacian comparison, and I just wanted to ask, the fact that the distributional meaning doesn't require much on the curvature of the ambient space, does that allow, like, can you replace sometimes barrier arguments with integral arguments and then sort of expand the class of manifolds for which it's true?
Well, no, I'm still using the, so I'm in the distributional case, the crucial thing I'm using is the fact that you have on the smooth part the inequality on the Laplacian rho square.
Oh, right, it's still in there. Oh, okay.
Yeah, it's definitely still there. Yeah.
Oh, sorry.
It's just that, yeah. So then the trick is that really it's just saying you only need to know that that holds on the smooth part in order.
Okay, to I missed it.
Yeah, that's right.
Can I ask a question?
Yeah, please.
So when you compute the Laplace of the distance function, so you use that Ricci is positive, right?
Yeah.
So I wonder if we can do some similar result when Ricci is bounded from below by some negative constant.
Yeah, right. So there is a version of the Laplacian comparison theorem which holds for any lower Ricci curvature bound, essentially by the same argument, right? So this picture that I have here with the constructing a family of curves by taking variation, essentially that this T here is telling you how far to push the curves off gamma as a function of T, right? So if you have a different lower Ricci curvature bound, then what you do is replace that T by the length of the Jacobi field in the model space with that Ricci curvature. Then you still get the same inequality. So what you get in the end is an inequality which says the Laplacian of the distance function on M is less than or equal to the Laplacian of the distance function in the model space with that Ricci curvature. And so the constant curvature space with that Ricci curvature at the same distance. Yeah. So it's exactly that inequality. Yeah.
So that then gives you, in the case of positive Ricci, gives you a sharper version of the inequality you proved, I guess.
No, in the case of positive Ricci, strictly positive, yeah, it'll give you a strong condition. Yeah, that's right.
But you can't have strictly positive in the non-compact case, right?
Indeed, yeah. So yeah, there's no interesting questions about harmonic functions of polynomial growth if you have a strictly positive lower bound on rigid. Yeah.
Yeah.
I just missed a point, which I probably just didn't notice. How do you get the when you're doing the Boostman function, how do you get that the Laplacian of rho is less than or equal to 0?
Oh, yeah.
How did that happen?
Where am I here? Yeah, okay, so we have really, okay, so you should think of this as saying really maybe a sequence xk, right? And we cook up these row k's, which are cooked up from the distance to xk in this way. And so the way I've chosen it here is that if you plug in the point x here, then you'll always get r plus epsilon, right? At point x naught, at the center of the ball, you'll get r plus epsilon for all k. And you also have a bound that the gradient rho k is less than or equal to 1 for all k, because they're just distance functions. And so that means if I take the limit as k goes to infinity, I get just by Arcella Ascoli, essentially, I get a limit rho which is still Lipschitz and still satisfies the Laplacian inequality, at least in the barrier sense, or in the distributional sense. And the inequality that it satisfies is, okay, so for each k, I had this Laplace rho k bounded by n minus 1 over rho k, but now the rho k, which is the distance to xk, goes to infinity. If I send xk off to infinity, and so that right-hand side just goes to 0. Yeah.
Ben, can you, instead of cooking up this eta, you mentioned the relationship to the first eigen function. I mean, can you just plug in something like Payne-Weinberger? I don't know.
Well, the trouble is you really don't know much about what these balls look like, right? They certainly don't have to be convex. So that, yeah, it doesn't simply follow from
gotcha,
the classical results. Yeah. In fact, the bound I get here, so I get pi squared on 16r squared. See, the diameter of this set is almost 2r. So you should think of this as pi squared on 4 times the diameter squared. That's I think that's actually sharp in this situation. Even though it looks like you're missing a factor of 4, but I think there's actually situations where that's sharp. I guess the picture would be if you had a manifold which is like a very long, thin cylinder.
Yep.
And then your ball, your x was somewhere here, so that the ball was this stuff here. Then this would be something close to the actual eigenfunction, I think. Anyway, yeah, I mean, there's lots of ways you can do this. In fact, Lee and Shane, first of all, prove a p equals 1 Poincare inequality just by a different sort of integration by pass argument, and they bootstrap up from there to get this one, which is a p equals 2 Poincare inequality. But and there's versions of this. Okay, so I use the fact that it's non-compact. If it's not non-compact, but you just know, you need to know that outside the ball of radius r, there are some points of some distance, and then you get an estimate which depends on sort of how far away the furthest point is, or something like that.
Thanks.
But we only need this case. Yeah. Okay. Good. Well.
Can I have one more question?
Of course.
So
yeah.
This is for entire harmonic function case. So
yeah,
is there some analog result for ancient solution to heat equation, say caloric function?
Yes. Yeah, that's right. So in fact, that's kind of the reason why we're doing this, is because so this result goes back to 1996 or so. More recently, there's a corresponding result for ancient solutions of a heat equation. And in fact, I think Julie's going to talk about that in a few weeks. But one way to deal with that is simply to reduce it to this result about harmonic functions. You can more or less reduce the result for ancient solutions of the heat equation of polynomial growth to the question about harmonic functions of polynomial growth. Yeah, so that, I mean, I think we're aiming to cover that too in the next few weeks. Yeah. Yeah. Otherwise, this is a little bit off topic for ancient solutions. Yeah. So yeah, I mean, it might be good for me to post up the other references. I guess I mentioned this. Did I write those down? I didn't know. So there's the one that I'm following mostly is by Peter Lee, and it's called Harmonic Sections of Polynomial Growth. Published in Math Research Letters, 97. And then there's also, I think, so Paul put up the reference to the JDG article, which was followed shortly after by article in Annals, which has the general result by Colding and Minicozzi. So that's also good to look at. In fact, there's all the beautiful methods in both of those papers, but which are quite different from what I'm talking about here, really.
I'll put the links somewhere convenient.
Yeah, okay, that'd be good. Yeah. All right. No more questions? Good, all right. Yeah.
Oh, okay. I was...
Go for it.
And
Has
you know
been-
any references that discuss any kinds of, not comparisons, but maybe almost comparisons for higher order derivatives of the distance function?
No.
Okay.
I guess you could probably prove something with bounds on higher derivatives of curvature, but I've never really looked at how that would work. But...
Well, it's a bit awkward because well, I don't know, maybe I'm not very good at it, but if I had a naive go a while ago and seems to require just assuming that gradients of the curvature have a certain sign, it just doesn't make sense.
Oh, okay, yeah.
So I thought maybe someone has done it properly. That's why I asked.
I could very likely has been done somewhere, but I don't know any good results.
All right. Thanks.
Thanks, Ben.
Okay, see you next week.
Thanks, Ben.
Thank you.